maintain proper attitude, and we will need to relay live down to the ground velocity, altitude, and pressure with our vehicle, and all of our motors need to undergo testing, both small scale and large scale. Some of our technical requirements, due to the past mixing and manufacturing done here at SLU, we will be constrained to doing a solid fuel design, just due to the success here that they've had. We will need to withstand loadings and account for the safety of the participants and anyone else in the surrounding area. We will need to have a tracking system that can recover up to 10 miles away in case we were to tilt and go off a little bit far. And then we need to record up to 120 minutes of data while we're in flight, and that's using our internal power. Then we need stability between 1.2 and 1.8 calibers for both stages of flight. And on our descent, we want no greater than 50 feet per second with the drogue chute and 20 feet per second with the main chute.
So our mission profile is very straightforward. As in any rocket, we do a systems check before takeoff. Stage 1 ignites, launches the rocket. When it gets to roughly 20,000 feet in the air, stage 1 burns out. And at that point, both stages separate. A 4-second delay, and then stage 2 starts up. Coasts up to apogee around 60,000 feet, and then at the same time, both our drogue chutes deploy and coast back down the main chute and land safely, hopefully.
So conceptually, we've drawn a lot of inspiration from 2 previous senior design projects. We have Centurion, which was the 2-stage you heard about from the last group, but also Billiken 1, which was an all-aluminum single-stage O-motor rocket that was simmed to go to a similar altitude that our rocket is going to. Unfortunately, that rocket had motor issues and was unable to leave the pad, so we are stepping up to the plate.
It left the pad.
If I remember, it got about 10 feet, right?
Well, some of it got up to a couple hundred feet. But,
so here's our mostly final design for what our rocket will actually look like. As it stands right now, our total length will be about 11.5 feet, including our 24-inch nose cone. And our stage 2 length will be about 6 feet. And the other important parameters is that our total weight will be about 115 pounds, and our upper stage weight will be about 24 pounds. And so these were originally designed using OpenRocket, and then the motors were verified using the BurnSim software, and we'll talk about those a little bit later. And then our transition length will be 4 inches to go from the 2 diameters of about 4 inches, and that's a commercial off-the-shelf standard diameter, and our stage 1 airframe diameter that will be out of the wound carbon fiber versus the fiberglass airframe sections. And our motor casings will be made out of aluminum, whether they are store-bought or not.
For our materials, we looked into wound carbon fiber, fiberglass, and aluminum for the actual tubes. Wound carbon fiber and fiberglass won out because they were the most cost-effective, weight-effective, and easiest to maintain. Aluminum, it was a little bit difficult for us to manufacture as students, as well as it had quite a bit of a weight gain.
As for the nose cone trade study, it was an easy one for the wound carbon, as it had the best aerodynamics performance as well as the supersonic flow. So it was an easy decision for us to make.
So as far as the actual mechanism of stage separation, we considered quite a few options with varying degrees of danger and complexity. And we ended up on drag differential, in which we have a coupler that will be essentially separated by the drag acting on the lower stage after the lower stage motor burns out. And the reason we chose that is because, for one thing, legacy. We know that Centurion successfully executed that form of separation, and it is also the simplest, cheapest, and safest option available to us.
As for the non-technical factors, we got the health concerns, and since safety comes first, we gotta follow the chemistry department rules and guidelines while mixing the propellant, as well as we're gonna have the mandatory personal protective equipment such as masks coats and safety glasses. As for the launch portion, we're gonna stay in a designated area. While launching, we're gonna follow the Spaceport America guidelines, and for the rocket itself, we're gonna have a proper tags of removed before flights for the ignition system and whatnot. For the subsystems, we got the propulsion part, where we're gonna design the two different motors using characterized propellant formula. We're gonna read mixing sessions. We're gonna design mixing sessions to create the actual motors. We're gonna have test firings, full scale and also small scale testing sessions before launching. For structures and stability, we're gonna design the transition section and verify it successfully, separate from the drag differential while maintaining the fit stability first fit stability. We're gonna design and run the cylinder carbon fiber winding of the transition section, coupler, and as well as the lower body tube. We're gonna design and manufacture the VIN geometry using fiberglass sheet. As the avionics bay goes, we gotta develop and sample the components such as altitude data, GPS tracking system, and radio. We're gonna prepare the ignition system for both stages, as well as the, in addition to that, we're gonna have the go, no-go margin, and it should be between plus or minus 6 degrees from the vertical as a reference to the Spaceport America. We're gonna prepare the electronic firing system for recovery blast charges. And lastly, we have the recovery portion, which we're gonna design and test blast charges to shear pins specifications. For each stage, we're gonna verify all the shock cord connections are successfully secured, and so on. We're gonna track the flight through, we're gonna track the rocket through the flight to final recovery.
So our manufacturing process is very similar to Lars. Thankfully with SLU, we have a lot of equipment here, so a lot of it's in-house. For our carbon fiber materials, we're using an X-winder. We'll be making the first stage for airframe, for the body, as well as the transition section. The fins we made out of G10 fiberglass, which were cut out of plates. And then for our optimized nozzles for the motors, we'll be using graphite stock. For our motors, we'll be mixing it with the help of Dr. Buckner for its safety and clearance. And then for the only purchasable options, we'll be using the nose cone. We'll buy fiberglass body tube for the second stage, so we get feedback in mid-flight, then the parachutes, and then the motor casings also.
As Cole mentioned, we have multiple plans for our motor casing, in particular the first stage motor casing, which is one of the more mission critical components of our flight. Our primary plan, the plan we hope to go with, is we will purchase an O-class motor casing from Loki Research, which is a vendor we have had experience with in the past. We've received a quote from Loki, and they are telling us that the casing will be around $3,000. Purchasing the casing allows us to greatly reduce risk, as we will be flying a casing of a proven design, and also greatly reduces the labor and testing costs, because we don't have to build it ourselves, we don't have to do the machining, and testing is reduced also as a result of the proven design. But while we are planning on purchasing this, this is dependent on fundraising success. In the worst case scenario, where we do not raise the necessary funds to buy the motor casing, we have a contingency plan where we will manufacture the motor casing from aluminum stock tubing purchased from Online Metals. This greatly reduces the cost, around $500 to less than $500. However, it obviously greatly increases the risk, as we would be designing the casing ourselves, and we would have to verify all of our work, as well as greatly increasing the labor costs. It takes a long time and a lot of money to perform that machining work, and we would be held to a lot of testing and verification requirements in order to maintain our safety. Safety is number one, and this is something we are very aware of following the events at the University of Idaho a few years prior.
So we have some particular constraints of if our final goal is reaching 60,000 feet apogee, we have 4 main constraints, but really it's 3. The 4th sort of comes into play for more earlier design decisions, and it's our weight, some of the particular geometries of our manufactured materials, as well as specific regulations. So the regulation that we have to abide by is the total impulse of a rocket that any just normal civilian can manufacture. At Spaceport America, we have an infinite flight ceiling, and we're very lucky that we were able to get accepted as a demonstration flight. But the key consideration is that we cannot build a rocket that has a total impulse of over 40,960 newton seconds, and that would be either 100% O or a 0% P, if you want to talk about it. And we cannot fire one unless we have an FAA AST license and certification. We are just students, so we don't have that certification, but we need to take this into account whenever we change our design or change our conceptual design for our motors, for our structures, or even for something as small as the fin span, because all of that changes our total apogee of 60,000 feet. So when we're doing our design, we always make sure that, or we have always been making sure to only change one thing at a time, take our altitude, take some of the important stability characteristics, because that's the key, stable and reaching our altitude.
So for our aerodynamic performance and analysis, our primary tool for analyzing the performance of our rocket was RAS-Aero, which is a free software that specializes in rocket performance at higher speeds. Under generally ideal conditions at average wind speeds for Las Cruces in June, we are simming to a max altitude of around 59,000 feet. And our peak Mach number happens during the second stage of flight at around Mach 2.7. Now, to get up to those altitudes and speeds, we of course need our motors. So for our first stage motor, this has been designed in BurnSim. We have an 86% O motor with a total impulse of around 38,093 newton seconds and a specific impulse of 189 seconds. The motor is constructed with 4 Bates grains and a moon grain right behind the nozzle. The moon grain has a center offset of about 0.3 inches, and the purpose of that grain is to reduce erosive burning during the burn. For the second stage, it's a bit smaller, where it's constructed out of 3 grains, all Bates grains. Total impulse of 5,169 newton seconds. It's a 1% M with a specific impulse of 191 seconds. For the ignition of this stage, in order to comply with Spaceport America regulations, we will be tying the ignition of this to a go, no-go system with plus or minus 6 degrees off of vertical, and we'll get into that a little bit later.
So for our mass budget, as any old rocket, propellant is majority. It is about 73% of our mass, followed by our structure for the fins and body tubes and nozzle, and then followed by avionics.
So for our stability, we configured the rocket originally in OpenRocket because of the ease of configuring our design. The entire configuration of the rocket, both first and second stage, has a stability margin of static stability of around 1.32 calipers. The CG is located 100 inches behind the tip of the nose cone, and the center of pressure is located 109 inches behind the tip of the nose cone. For just the upper stage, we are getting a static stability of 1.44 calipers. And the CG is at around 49.9 inches behind the tip, and the center of pressure is about 56 inches behind the tip of the nose cone.
So for one of the first steps for stability is fin flutter. Since we are going supersonic, it is going to play a factor. We use this equation. There was another one I found, but it did not take into account supersonic flight. So using the aspect ratio, static pressure at altitude, tape ratio, thickness, and so on, take into account the highest apogees for each stage, For stage 1, it is going to be around 25,000 feet. At that high altitude, velocity of flutter is at 91 feet per second. Because of how it reacts, you need a higher velocity to cause flutter as you go up in altitude. So when we launch off the pad, we're actually going around 75 feet per second. So we'll actually be exceeding this velocity before we even get there. And it'll be the same with stage 2 at 60,000 with the velocity at 619. So we will pass the flutter margin.
So this is a plot of the rocket's stability in calibers over the time of the flight. A few important points here. You can see that during the entire flight, the stability is above 1.2 calibers, and it also steadily increases. This vertical line right here is actually where the stage separation takes place. The stability starts increasing again until the second stage motor ignites, at which time it does a slight wobble. So you see a little dip there in the stability, but then it increases and keeps going. And this is a plot of the pitch angle of the rocket. Now, an important thing to remember about this plot is that this plot actually assumes that we would be experiencing wind speeds of 17 miles per hour, which is more than twice the average wind speed we actually expect in New Mexico during that time of the year. And it was recommended to us that at the time of second stage ignition, our rocket would deviate no more than 6 degrees from vertical. And in this 17 mile an hour wind regime, our rocket at second stage separation is 83.6 degrees from horizontal, so it deviates less than 8 degrees from vertical. So we're very confident that in the actual much smaller wind speed regime, we will be well within that 6 degree margin. As far as our structural assessment goes, we've essentially determined the materials we intend to use with pretty much complete certainty. We still need to finalize the exact measurements of the body components and the fins, so we can determine the exact locations of the CGs and the CPs for both stages and for the entire rocket. And we've already verified our current measurements using the open rocket and the brass arrow, and in addition to that, we've also created the model in Autodesk Fusion 360. And we have two main questions that we need to answer before we can launch, and those are, can the airframe handle the Gs of the above Mach 2 regime that we'll be experiencing during flight? And we intend to determine this by doing simulations of the loads caused by lift, drag, and gravity. We're going to do computer simulations and physical tests. And we're also going to look at legacy designs to see how other rockets have sustained the loads they experienced during flight. And the second question is, can the stages actually separate? And we're going to determine that by doing a force test on the coupler, in which we're going to use either an accelerometer or a force sensor, and we're going to pull apart the coupler, and we're going to determine how much force is actually required to pull that apart. And then we're going to see if the drag the rocket undergoes is enough to meet that force requirement.
So for power assessment, for our rocket, there's not much power actually being involved. We had to double up one for each stage essentially. So each stage we use a Raspberry Pi as well as a featherweight GPS. The featherweight is a necessary component that Spaceport America asks us to use. Current requirements, it only has 25 milliamps and 90 milliamps for each. It gives us a total of only 680 milliamps. For battery, we have not looked into that quite yet until we actually buy materials and test them to see what actual capacity we need.
So some developmental testing. As of right now, we have 3 main tests that we need to complete before the actual full-scale launch in June. Particularly the 2 propulsion tests, so small-scale propulsion tests based off of each mixing session to make sure that all of our motors are meeting compliance of the theoretical impulse per mass, and then full-scale propulsion test for both stages, and that will be done around April. So we want to make sure that our full-scale size of theoretical motors meet the requirements of our thrust per mass and just general total impulse. And then, like what Dakota said, we have our stage separation and we don't have a specific day that we have that planned, or a specific month that we have that planned, because that, along with the other structural assessments, will be done throughout the semester, because it's a manufactured part that is a easily changeable part. And then we will also be doing recovery blast charges testing in March to make sure that our full recovery deployment is successful and we won't come up with any complications. So some risk assessment and mitigations. Our main concerns that you see are A, F, and H. And F we split up into two different sections for the upper and lower stage. A are catastrophe takeoff, a CATO. F, a unsuccessful recovery subsystem deployment. B, the failure of separation, and H, the significant motor underperformance. All of these, while they are particularly relevant to the actual launch of the motor, can all be mitigated through design. So for a CATO, we need to follow all legacy and Spaceport America regulations as to how to launch a high-powered rocket and how to design a high-powered rocket, doing all the testing for a high-powered rocket. So that's to mitigate any of those risk factors. For B, a failure of separation, again, we'll be going to be doing those structural tests to make sure that the theoretical drags experienced will be able to induce a friction separation. For unsuccessful recovery subsystem deployment, again, more testing to make sure that our blasting will deploy, the amount of loads that we will experience will be able to unfurl and properly inflate a drogue or main chute, and to use things like a Jolly Logic altitude release mechanism to deploy the main chute. And then finally, H is significant motor underperformance. That can be verified using the 38 millimeter propulsion tests, because they come from each individual mixing session. We can determine that the full-scale model will experience similar loads and similar impulse to the small ones.
This is our Gantt chart. It encompasses both first semester and second semester. Please make note that everything to date has been accomplished. If you're looking for that, it's roughly in the middle where it says fall final report. We are looking into ordering all of our materials and collecting them by the end of January. March 6th, we're hoping to do a small scale motor testing, and by the end of March, we're going to do a full scale motor testing. We are looking into April doing a small scale stability test to ensure that the fins keep us pitch right, and then we're going to go to the Spaceport America competition in June 16th through 20th.
So some requirement compliance. The top four requirements have all been at least theoretically verified using our computer modeling as well as calculations that we've determined. So they tentatively have a check that we meet those requirements. However, we have the two main requirements of testing, which goes into being prepared for the final launch. These are already planned in the Gantt chart, as Camden just mentioned, as well as if we are able to actually get if we are able to purchase the O motor for the first stage, then that greatly speeds up and greatly affirms that we'll be able to do these full-scale motor tests.
Our budget and fundraising, right now we are currently going through Billiken backers for funding, and we are looking into small aerospace companies to get sponsors. If you look at our budget here, $7,900 is the approximate cost of the entire thing if we are to purchase the motor casing that we would want to. If we were going to make it in-house, then it's going to cost us $5,100. We consider that part of the structures with the $3,800 and $1,000.
How much do you have? As of this time, with the $500 budget that we were given by the department, we're around just shy of $2,000. So we've got some work to do in the fundraising department.
This is our presentation. Thank you for coming. Are there any questions?
So for the competition, is this the Sonic Rockets part of the competition, or you're just going to have
We're just going as a demonstration.
We're flying an exhibition flight at the competition.
Right. Cool.
So it still has to abide by all the same application rules.
Right.
Um,
I didn't know if you were just shooting for 60,000 and like past years you had you lost points for not getting it. So
No, the
so getting off the pad and launching is like
the category the categories for spaceport are 10,000 and 30,000, and then they usually have a couple every year that are demonstration flights. Billiken 1 2 years ago was a demonstration flight in addition to the club team, which was doing a 30,000 foot or a 10,000 foot, and that's the same this year. The club is also going.
Or maybe a demonstration non-flight.
I mean, the nose cone flew.
The nose cone
Not
did fly,
yeah.
yes. It worked as a cannon.
the
They've
video
also
is
got-
pretty cool.
They've also got separate categories for in-house constructed motors and off-the-shelf
Right.
motors. And we will be not in the competition, but we are building our own motors.
Sure. So beyond that, so talk to me about, so we get up and you do the separation. How are you going to ensure second stage maintains a vertical profile?
So we are required by Spaceport America to use one of a few flight computers to verify our pitching angle. It's called the Featherweight GPS system, but it's more than a GPS, it's a full sensor package, and that is one of their recommended systems that we are using.
So in your wrists, I don't think I saw, you blew through really quickly.
Yeah.
The separation, second stage emission off altitude.
Altitude.
Well, is altitude or is it attitude?
That's an altitude
Okay.
target, because the attitude is corrected via the static margin of between 1.1 and 1.5 static margin under subsonic flight. A rocket will actually self-adjust by pivoting on the center of gravity and the fins creating lift and drag to then center itself.
So you're
that's
pretty
why
much assuming when you get to your separation altitude, whatever that is,
Mhm.
you're going to be in a vertical or mostly vertical.
The reason why we have that 4-second delay is because we don't necessarily know that we're going to have exactly vertical, but it gives the rocket itself
The
time
ability
to adjust. Yeah,
and-
and so that was also determined in our pitch angle a little bit earlier, that even with heavy gusts that would actually impede the self-righting, even in heavy sustained winds, close to like Midwest or Northeast, like storm level winds, not hurricane, we're still within our acceptable margin of that plus or minus 6 degrees, and that has both been a standard as well as a like direct requirement from Spaceport America. So both of those say, okay, well, we need to be
So
between
it's going to be, if I remember correctly, so you separate, you're doing like 1.7-ish, you slow down a little bit, and then you
here,
blast, which is
so-
kind of cool.
yeah,
Everything- so
there's a lot of graphs.
there we go. You're good.
Yeah.
Yeah.
So this is like
2.4. Okay,
yeah,
I was
so this-
remembering a different chart, right?
Yeah, so this is the end of first stage burn, and while we say in our requirements that we want to separate nearly immediately, we understand that supersonic flight or supersonic flow, a lot of funky things sort of happen. So we're not saying that it needs to separate at exactly the stage or exactly at first stage burn out. So that's why we're allowing the 4 seconds for writing and the 4 seconds for just making sure that it's that the first stage is completely separate from the second stage.
Very cool.
What is your make-buy risk on your case, not on your risk queue? You opened up your presentation talking about it.
Mhm.
You clearly, it's one of your biggest execution risks for cost,
Mhm.
but it doesn't show up on your risk.
We developed our risk analysis chart before we had learned of the larger cost for the motor casing, and we should have included it. I'm sorry for that. Yeah, this news was not very recently, but like recently enough that it's put a couple things.
Yeah, I
a little
look
bit
forward
differently.
to your risk mitigation plan on that one.
Can you go to your floater chart?
And we refer to the line.
That one?
I'm curious about that.
Other way.
So, two things with it. How did you assess the shear modulus, or I guess the stiffness aspect of it?
Shear modulus, so we assume we were using G10 fiberglass, so I went online and found the rough numbers
And the other one was, I believe you quoted, you're way past your flutter margin, which to me, are you well within your flutter margin? Or
And
you-
it was from the data I collected, it was the flutter margin should be below the speed of what we're at. So if we're at 91 feet per second, the velocity would be the altitude of where we're having this velocity at 91 feet per second should be pretty close to above ground level. So we should be past it before it hit the rock.
So yeah, we're already above the speed at which flutter occurs, and so we don't expect that it will, or we expect that we will at some point experience flutter, but we're not staying at the sustained speeds of causing.
So to me, flutter is, when I think of flutter, I think of a divergent phenomenon. It's gone. Like, so when you say you're already above flutter speeds, to me that would be a no-go.
Right.
Yeah.
You lost the tail.
Yeah.
For a supersonic flow, the flow separation would be much more of a structurally significant change in fin flow than the flutter itself. I'm not aware of the flutter that occurs on an airplane, more in rocketry, and if those have the same meaning, then clearly that's a problem, but I'm pretty sure that they are slightly different.
So it's like more like a buzz or a.
I think so.
So you're supersonic, but you show Mach at .09 and Mach at .6.
So that's when the flutter occurs. So we're already past like the base.
That is the flutter speed that we calculate. I just converted it to velocity, so we see what we see.
Yeah, I'm not sure that's coming out right.
Yeah, that's like blowing on a piece of paper low. You're there.
Yes.
So.
Something doesn't seem right there, and I can't tell you off the top of my head. But the other thing is, you're looking at supersonic, but your worst case flutter could be a transonic, where you've got oscillating shocks going on.
Even though they're blown through really quickly, but still, yeah.
You're not going to be going through it quick enough. So they've looked at this year after year, so I'm definitely not my expertise, which you may want to look at. You've got something to say, I can tell.
And a lot of our.
No, I agree. I think it's
So what's your biggest risk? Sounds like the separation. I'm going to give you your answer.
Yeah.
Right?
Yes.
Separation. So I'd almost recommend like a brainstorm. I mean, you seem to have identified it, but really sit down and say, have we really thought of all the things that can impact? Because I haven't heard anything about thermal. And to me, I mean, I guess I don't understand your separation approach. You kind of went through that quick. So you're relying on drag. Are you deploying something on the bottom stage that makes it more draggy? Or
So the bottom stage is at a larger radius.
So you're just saying it's naturally.
Yeah, it will naturally once the
thrust stops.
Yeah.
Got it.
So because the connection between the lower stage with the transition section is just a press fit, it's not pinned in or screwed in. So that which we were trying to determine in second semester with those gauges is that the friction will be enough to hold it while it's in flight, but when it's not in powered flight, it just drops.
That's the drag difference between the two. Well, there's quite a bit of drag on the front, the first or second stage too. So you may want to think about that, but I didn't see anything on thermal. I mean, thermal can impact how that friction between those two joints, and I don't know if there's heating going on because of the solid rocket, but you're definitely getting cooling because of the altitudes that you're going to. So I don't know if thermal, or maybe you have some type of sleeve that's not affected as much by thermal. But you may want to look at thermal, and the other thing is bending loads through your system can also be impacting that friction between the two.
Especially at our coupler and transition section.
So something to consider.
Yeah, we'll look into that.
Oh, and then the last thing, sorry, you talked about you had to stay below a certain thrust level to be able to launch this, and it sounded like you were well below that.
For the total impulse?
Yeah.
We are right about at it at the moment. We're actually just a hair above it. As we go forward in optimizing our design, we're going to be.
Oh, then I didn't add up correctly.
Yeah.
Never mind.
So 38 and 5 were the two stages. So we're about 42. So it's optimizing the motors, it's optimizing the structure, and it's optimizing other manufactured parts, because the size of the fin can impact the total altitude. So again, with the constraints, we're only changing one thing, and that way we can hopefully get a total impulse below the.
And that's analytical. Do you have to have any buffer in there or margin in there for analytical versus actual?
We're gonna get actual tested impulse numbers from our full-scale tests that we're going to be completing in April.
Yeah.
April and March.
And overall, like a key thing that we have, as a group, have discussed is that because of that hard cap of what we can legally manufacture, rather than just like functionally manufacture, we as a group are okay with a successful flight of, if the apogee is something like 55,000 or 54,000 feet above ground level, because 60,000 is not our hard cap. It's the successful supersonic deployment of a two-stage rocket in general is what our successful mission is.
Good.
You can always just get a mentor to help you with that that's got a license, right? I mean, lots of the teams in the past had a consultant that has the appropriate license.
There's been a struggle finding rocket mentors.
As well, this is a separate.
Class 3 license.
This is a separate thing from Tripoli license.
Oh,
this is FAA.
going to the
license.
FAA.
Yeah. So because we're launching at Spaceport America, the licenses are, or the Tripoli certifications are included in the fact that we are launching with that, or with ESRA, so the Experimental Science Rocket Association, at a specific competition. So we as a team don't need the Tripoli license or the Tripoli certification, but the FAA is a hard legal.
So is that just a bridge too far to go and try and get the FAA license? I know I'm
like a
way off
couple
reservation in
$1,000.
there.
It's a pretty big bridge.
Oh, it's dollar type of thing too?
Yeah,
It's a dollar
it's
thing.
There's an
expensive. It's a
application
lot of
fee
work.
and- okay, got it.
Yeah,
Forget
it's
it.
outside of the scope of it.
Step up, right? The professor should step up, so
If we're gonna have someone get that training, we need someone who's gonna stay here and use it multiple times.
Volunteering?
No.
I'm with them. I'd like to see this launch.
Yeah,
I would too.
We would too.
June 16th is the tentative date.
So your checklist needs to ensure O-rings are installed, and
Yes.
double check the O-rings installed, and then
We
once
need to
you've
make
done
sure that there's no unsettled bits
Okay.
within the motor.
I'm gonna step in. Clearly, we're moving the edge. Yes, it's a vertical pause. So a few quick points. First off, let's thank our panelists for coming here. Secondly, panelists, if you haven't got enough of this, the team that's missing will be presenting at 3 o'clock on Tuesday of next week in this room. Not really expecting you to come, but if you're really interested, you're welcome to come. I'm recruiting some other people to do that one, but you are welcome to come if you would like to do that. So that's the Horizon project, which is the micro SAE competition, but they had two people who could not be here today, so we pushed them off to Tuesday. As far as students go, remember that I will be distributing these to you, copies of these, on Monday, and part of your report is to respond to the comments that the panelists have made, and briefly say, hey, we think, yeah, they're right, or you are welcome to say, no, we don't think they know what they're talking about, and we're going to go off in our own direction. It's your project, but that's part of your final report, so please remember that. Final reports, again, are due the Monday of the exam week, so what is it, the 16th, is that what the date is, something around there. It's the 16th, so that's the last thing you need to do as far. I would appreciate, we don't technically requirement, but if you're willing, sending a copy of your slides would be quite helpful for future years as well. As you've seen, I've been able to share some of those, so an electronic copy would be helpful. And anything I'm forgetting? That's a wide open question, right?
Anyway, really well done. I think this is probably one of the better designs I've seen in years at this stage, right? So you guys really followed a good template, right? It was clear slides, great presentation skills. I really love what we call the OV1, the system concept, right? So too often in years past we would get blasted with, here's my design, and we had no clue what the heck we were doing, right? So really well done. hey, everybody's looking really sharp and loving that, right? So, you know, not as
You'll just have to check these.
I would love to see half the presentations at Boeing be as solid as what you guys just did. So, come on down, right? So,
Any other overall comments that people want to make before I dismiss the crowd?
Thanks for the opportunity, really appreciate it, great job.
well done, guys.
Thank you. All right. Thank you very much. And good luck on your exams.
What's the plan for the room?
We do have to restabilize the room. Well, reconfigure.
I don't want to reconfigure.
This is disconnected numerous times. Turn the tables back on. Yeah. Really the part of the
Oh, I would love to stay with that. I'm worried about getting home.
Thanks.
40 between